So remember, we've been talking about how we can use z-scores to compare data sets, right? But we can also use z-scores to figure out the actual amount of data or estimate the amount of data within a region. So that's what the empirical rule tells us, is that now something to pay attention to. The empirical rule says you have to have a symmetric bell-shaped distribution. So in other words, your distribution has to look something like that. Has to. So it has to have that bell shape to it. You've seen me draw stuff with that shape a lot already, but it has to have this shape to be able to use the empirical rule. It can't be skewed either direction. It can't be uniform. It can't be multimodal. It has to have this symmetric bell shape. But if it does, then you're going to have 68% of your data values within one standard deviation of the mean. Or in other words, 68% of your data will be between a z-score of -1 and 1. So in between those two z-scores, 68% of your data. Now I say about 68 here. The reason I say it's about 68, it's really 68 point some stuff. It's really 68 point some stuff. Later on when we get to chapter 7, we'll talk about how to find that exact rest of that percentage. But it's close enough you can say 68% of the data lies in that range. It's close enough. So 68% of your data is between z equaling -1 and z equaling 1. 95% of the data is within 2 standard deviations of the mean. So 95% of your data is between -2 and 2 for your z-scores. So see how we're kind of using those z-scores to kind of make a ruler now, right? And so we're kind of extending it out a little bit. Now remember what I said about standard deviations though, right? I said most of your data values would be around between 1 and 2 standard deviations of the mean, right? But really, most of your data is within 1. A lot of your data is within 2. And by the time you get out to 3 standard deviations, so once you're between z equaling -3 and z equaling +3, you have virtually all of your data accounted for. 99.7% of your data is going to be between z equaling -3 and 3. So remember when I said a good way to check a z-score most of the time is that z-score should be typically somewhere between -3.5 and +3.5, right? Well, that's because 99.7% of your data for a symmetric distribution is there. It's between -3 and 3. So what that means is the likelihood, if you start thinking about these percentages, it's kind of the likelihood you're going to be in this range. Kind of thinking, foreshadowing chapter 4 and 5 whenever we get there. But if you think about these percentages as the likelihood that you're going to fall in that range, that means there's only, if we've got 99.7% of the data between -3 and 3, what's the likelihood your z-score is going to be somewhere bigger than 3 or smaller than -3? 0.3%, right? Because that's all that's left over. So it's a tiny, tiny chance you're going to have a z-score bigger than 3 or smaller than -3. So most of your z-scores are going to be between really -3 and 3. And again, I'm saying about on both of these because it's very, very close to 95 and 99.7. It's 95 and some change, basically. It's going to round to 95% if we round to the nearest whole percentage. And same thing here, it's going to round 99.7. So even though I'm saying about, you can really think of this as being exact. And we will calculate the exact percentages whenever we hit chapter 7. So kind of pictorially, because I know I'm a picture person and some of you probably are too, this is the empirical rule in pictures. So same idea. So here's my, where you see x bar minus 3s, x bar minus 2s, etc. That minus 3, minus 2, minus 1 here, these are your z-scores. So what I'm really saying, you can really kind of think of this as being the mean plus or minus the absolute value of z times s, times your standard deviation, is really what you can think of each of these as being. It's either going to be the mean, if you're below the mean, it's going to be the mean minus your z-score times s, or minus the absolute value of the z-score times s. Or really, if you just look at it, here is your z-score. So the reason I'm kind of wording it as x bar plus or minus the absolute value of z times s, that's kind of going to set you up for where we're going later on in chapter 9, or no, 8. So kind of setting you up for where we're going with this stuff later when we start trying to build an interval. Although we're going to do some of it in this section too. So kind of setting you up for that a little bit, starting to think of how we get this. So if you think of it, so it's really going to be either x bar minus some value of z times s, or x bar plus some absolute value of z times s. Now the reason I'm doing the absolute value here is indicating that operation. But realistically, if you look at it, what you see here between the x bar and s is your z-score. So what you're seeing there is the z-score. So this would be the place where z is -3. This is the place z is -2. Z is -1. Here you don't see z at all, or you don't see a number at all, so z is 0. Z is 1. Z is 2. Z is 3. Which kind of makes sense, right? If you think about what we're saying here, we're saying you're at the mean and then you're 1 standard deviation above it, right? Remember, that's what that z-score of 1 means. Here, you're 2 standard deviations above the mean, 3 standard deviations above the mean. And same thing down here. You're 3 standard deviations below the mean. So these are saying the same thing. They just look a little different. So basically, this would be how you would get back to the number if you had that z-score. This is that z-score. Now, because this distribution is symmetric, so the empirical rule gives you those 3 percentages, 68, 95, 99.7%. But because it's symmetric, we can actually split it up and find basically any combination of these regions. We can find the amount of space in those different regions. So, for example, because we know we have 68% of our data between -1 and 1 z-score, right? Because it's symmetric, that means there's going to be an equal amount of space on both sides. So there's 34% here and here. Similarly, if we extend that out, right, so we know we have 95% on either side or between -2 and 2, right? So then if we cut that in half, you end up with 47.5% on either side. But accounting for the fact that we know 34% is between the mean and 1 standard deviation on either side, right? Then we can subtract that off to get the 13.5% here and here, right? And same idea to get that 2.35% between 2 and 3 on both sides. Now, what this picture doesn't show you is that other piece that's out here, right? So we can't forget about that piece because sometimes you might need it. So, for example, if I said find the percent of data values that lie above 2 standard deviations above the mean, right? Then we need to know this percentage also. We need to know what's out there beyond 3 standard deviations in either side. So you can still get that the same way, right? So we know we have how much of our data left over after we go out beyond 3. We've got 0.3 left, right? And then we split that up between the two sides. So what do we get on either side? You're going to get 0.15 on either side, right? So you get that also from this. So I'm not going to say you have to memorize all of these little percentages. You don't have to memorize every single one of those percentages if you know how to recreate it, right? So as long as you remember the 68, 95, 99.7, and you can recreate these percentages, then you don't have to memorize them. But you've got to either be able to recreate it or know those percentages, one of the two for now. Once we get to chapter 7, I'll show you a way that you never even need to worry about this anymore. Other than the fact that it can be a way to do it quicker. All right, so let's look at an example where we use the empirical rule to find the percentages. So in a survey conducted by the National Center for Health Statistics, sample mean height in women for United States ages 20 to 29 was 64.3 inches with a standard deviation of 2.62 inches. So we want to estimate the percentage of women whose heights are between 59.06 inches and 64.3 inches. Now I'm going to go ahead and warn you ahead of time. Do not look at how Hawkes solves these problems. Do not look at how your book solves these problems, because they don't relate it to z-scores, and they do it a little bit more difficult of a way. So I'm going to relate this back to z-scores because it makes it easier. Because once you know the z-score, you know where you're at here. So the way I recommend doing these problems is find the z-score for each of these numbers. Just find the z-score. So if I start with the 59.06, right, then how do I calculate that z-score? So data value minus mean divided by standard deviation, right? Always your score formula, regardless if it's a population or sample. The only difference is what we're calling the pieces, right? So here, what's my data value? What's my x? Okay, so either one of these numbers, right? Now I'm going to start with this one just because it's there. It doesn't matter which one you start with because you got to do them both anyways. So I'm going to start with the 59.06. And what am I going to subtract 59.06? 64.3 and divide it by 2.62, right? So we do that. What do we get for that z-score? -2. And so then you do the same thing for that 64.3. So if you do z equaling 64.3 minus 64.3 divided by 2.62, what do you get? You get 0, right? So what does that tell us? That tells us this data value, right? So whenever x is 59.06 inches, we're 2 standard deviations below the mean, right? And then what does that z-score of 0 tell us about 64.3? You're at the mean, right? You're in the middle. So what that means is if you go back to this picture, we now know where we are, right? We know we are 2 standard deviations below the mean, and we know we're at the mean. So then if you want to find that percentage between those two places, you add up the percentages between them, and that's all you have to do. So here, if I want to know that percentage, I'm going to add the 13.5% and the 34%, and that's going to give us what percentage? 47.5%. That's all there is to using the empirical rule. So what's the problem with the empirical rule? Yeah, it's only for a symmetric Bell distribution, right? Is every single data set in the real world a symmetric Bell distribution? It's not, right? Now, it's true most distributions are going to be symmetric in the real world. In practice, when we look at them, they are symmetric. But not every distribution is symmetric, right? So we need a way that we can estimate percentages or likelihoods or areas or probabilities, kind of foreshadowing where we're going with this stuff. We need a way we can estimate that for any distribution. So that's where Chebychev's theorem comes in at. Chebychev's theorems, now in general, Chebychev's theorem, I will say, is weaker than the empirical rule. But the advantage to Chebychev's theorem is it does not care what shape the data has. So that's the advantage that's the pro to using Chebychev's theorem. So the con is it's weaker than the empirical rule, but the positive of Chebychev's theorem is while it is weaker, it doesn't care about the shape of the distribution. So it works for every distribution. Now I worded this the same way as the book worded it. So the portion of any data set lying within k standard deviations where k is greater than 1 of the mean is at least 1 minus 1 over k squared. So what I want you to think about k as, think of k as the z-score without the sign. K is your z-score without the sign. So k is the absolute value of z. That's the easy way to think about this. So k is just your z-score without the sign. So in other words, find your z-score, ignore the sign of it, there's your k value. So the part you really need to remember for the test on this is really going to be k equaling 2, k equaling 3, k equaling 4. You really need to know these three values. On the homeworks, you're going to find some where k is not 2, 3, or 4, so you'll need to use the formula for those. But I will not give you any of those on the test. The ones I will give you on the test are going to be k equaling 2, k equaling 3, k equaling 4, keeping it to the whole numbers. So what k equaling 2 tells us, in any data set, there is at least 1 minus 1 over 2 squared. So there is at least 75% of your data value within those 2 standard deviations of the mean. So there's at least 75% of our data between z equaling negative 2 and z equaling 2. There's at least 75% of the data there for any distribution. Why did I say the empirical rule is stronger for a symmetric distribution? So for k equaling 2, right, or in other words, between negative 2 and 2 standard deviations away from the mean, with the empirical rule, we know there is really exactly 95 and some change % of the data there, right? So here we get an exact amount, or close enough to an exact amount. It's not going to be off by much if you say about 95%, because it's literally 95 point some stuff. So here we're getting an exact amount. What are we getting with Chebychev's theorem? 75. But is it exactly 75%? It's at least, right? So we're only getting a minimum percentage here. You're only getting the minimum amount of data that's guaranteed to be there. It could be more. It can't be less, but it could be more. So we're not getting the exact amount. So is this really true with the symmetric distribution? Is there at least 75% of your data between 2 standard deviations away from the mean? So is 95% at least 75%? It is, right? So it's still true. Both rules are true, but you're getting a stronger rule with the empirical rule. You're getting a stronger statement from it. Same idea, so k equaling 3, you would use the same formula, 1 minus 1 over 3 squared, to get 88.9%. So, but you get, again, a minimum percentage. So at least 88.9% of the data is between negative 3 and 3 standard deviations away from the mean. So here, z-scores, negative 3 and 3. Now again, with the empirical rule, you're getting something stronger, right? Because the empirical rule, where you know it's exactly 99.7%, or exactly 99.7 and some change %, right? So we know we're getting something stronger with the empirical rule. So if you have a symmetric distribution, which rule do you think you should probably use? Empirical rule, right? But if it's not symmetric, that's when I would go and default to Chebychev's theorem, because we don't have any other choice. And same idea now, so we go out a little further, k equaling 4. There you've got at least a minimum percentage of 93.8% of your data values lying in that range. So here z would be between negative 4 and 4. All right, so there's only two types of questions I'm going to ask you about Chebychev's theorem or the empirical rule. And that is, I can do one like I did just a second ago with the empirical rule, where I give you an interval and ask you to tell me the percentage. So I can do that. So I can either I can give the interval and ask the percentage or the number of standard deviations. And so in that case, basically, find the z-scores. So your process for solving with empirical rule and Chebychev's is really the same. So if I give you the interval like I did before, so I'll give you something where it's in terms of the original data values, and I say something between 59.06, 64.3 inches, something like that, I'm giving you the interval, and then I'm going to want you to find that percentage or the number of standard deviations. But in that case, just find your z-scores and use that to find the percentages based on where those z-scores are. So that's exactly like the example we just did. So I can give it to you that way, or I could give you the percentage, which really, if I'm giving you the percentage, I'm giving you those z-scores indirectly, right? And then you have to find the interval. So to find that interval, to get the data value back, if you have that z-score, x is equal to the z-score times the standard deviation plus the mean. Now in this case, notice I'm saying the z-score, right? So you want to know if that data value is above or below the mean when you're looking at this. The sign is important. But if I wrote this another way, right? So I'm really saying x is equal to x bar plus or minus ks is what I'm really saying. Or x is equal to x bar plus your z-score times the standard deviation. So that's the same thing as I wrote up here in words. It's the same formula. I'm just writing it in terms of k and z here. So if you know the z-score, you just multiply your z-score times your standard deviation, add your mean to that, because the z-score already takes into account the sign. If you don't know the z-score, if you know the value of k from Chebychev's theorem, for example, then k doesn't take into account the sign, so you've got to do both plus and minus to find those two numbers, right? But that's all there is to it. Here, I'll give you the age distribution of Florida. And so we want to apply Chebychev's theorem to the data using k equaling 2 and figure out what we can say based on that. I'm giving you indirectly your z-score, right? So k is 2, which means z is positive and negative 2, right? Which also gives you your percentage, right? So what percentage do we know? So we know at least 75%, right? Because we know k is 2 or z is positive and negative 2. And the nice thing about Chebychev's theorem, if you know one of the z-scores, you know both z-scores. With the empirical rule, you're not guaranteed that. You can have any mix of 1, 2, or 3 standard deviations above or below the mean. With Chebychev's theorem, it has to be the same number. So it has to be positive and negative 2. I can't split it up like I can on the z-scores. So if you know one, you know both z-scores for Chebychev's theorem. So we know at least 75% of our data values. And then I'm asking you really to find the interval, right? Because we don't know that interval that those data values are between. So where is at least 75% of our data? So then that's where you're going to do x bar minus, or sorry, in this case, because I gave you population data, mu minus 2 times the standard deviation for that lower number, and mu plus 2 times the standard deviation for that upper number. So notice mean minus KS, or mean minus K standard deviation, right? Mean plus K times the standard deviation. So notice there's that formula that I gave you, but it's still between mu minus K times standard deviation, mu plus K times standard deviation, right? Which also coincidentally is the same way I wrote it here, right? Mean minus, if you think of this number as K, mean minus K times standard deviation, mean plus K times standard deviation. Or I wrote it here as absolute value of Z, right? But same idea, because absolute value of Z is K. So in this case, that means our lower bound for this interval, where at least 75% of our data lies, is going to be our mean of 39.2 minus 2 times 24.8. And so if we calculate that, what do you get? You get negative 10.4. And we're talking about age here, so that's negative 10.4 years old. So let me ask you this. Does that answer make sense in terms of our data set? We're talking about age, right? Yeah. We know age is at what level of measurement? Ratio level of measurement, right? Because that 0 is a hard stop, right? 0 means if you have 0 years of age, you have no age, right? You cannot go beyond that 0. So this doesn't make sense in terms of our data, even though that's what the formula gives us. So in this case, we're going to use, even though we got negative 10.4, we're going to use 0 years old because that's the smallest possible data value you could have, right? So we're going to say at least 75% of the data lie between 0 years old and then we calculate the upper bound. So data value plus 2 times standard deviation. So same numbers, right? So 39.2 plus 2 times 24.8. And what do you get? 88.8. And does 88.8 years old make sense? It does. You can have that as an age, right? In this case, so at least 75% of the data lie between 0 years old and 88 years old. That's what we can conclude. Or if you really want to take this a step further, instead of saying of the data, we know what that data is, right? So what is our data? Ages of Floridians, right? So we can say at least 75, instead of saying of the data, so you would use something like of the data if you don't know anything about your data. But if you know about the data, talk about the data. So here we could say at least 75% of Floridians are between 0 years old and 88.8 years old, right? So then if somebody were to just look at that sentence, it tells them everything they need to know about that, right? Based on Chebychev's theorem.